So today we are going to continue the discussion about pruning and sparsity. So in last lecture, we have go through the basics of pruning, and in this lecture, we are going to cover these more advanced technologies, right? So how do you select the pruning ratio, right? The deep neural net has many different layers. VGG has 16 layers, Reason 50 has 50 layers. Are all the layers equal? Do you prune them in a similar sparsity ratio for each layer? That's actually not the case. And how do we select the sparsity ratio for each layer, right? That's the first topic. And then how to fine tune to recover the accuracy, right? Do you increase the learning rate, decrease the learning rate? How to do that? Do you prune everything at once? Do you do them gradually? So that's how to fine tune the pruning model. Next, we are going to introduce this logarithmic hypothesis, okay, which is showing that training a sparse neural network from scratch is sometimes possible, right? And finally, how do we realize those speed up, okay, by pruning using different granularities, specialized hardware? We'll talk about that in the later part of this lecture. Okay. So just go through what we have learned. Where are we now? Like we have already covered these 3 points. So what is pruning? Reducing neurons, reducing the weights, okay, and determining the pruning granularity from fine-grained pruning, where we can prune more, to the coarse-grained pruning criterion. And now we are here, okay, determining the criterion ratio, and then also fine-tune and prune neural net. So pruning, basically removing synapses and neurons, just as an overview, getting pretty popular in recent years. And it has been widely adopted by the industry. For example, if you have an A100 GPU, sparsity 2 to 4 sparsity is already supported over there. Okay, and Xilinx is also using that. So we talk about the setup, which is basically minimizing the loss function subject to the number of non-zero weights should be smaller than the threshold. And we discussed the different granularities of pruning from the fine grain to the coarse grain, where we can prune the most, where it's easiest to accelerate. Here requires specialized accelerator to accelerate, versus how to select which synapses to prune. The magnitude-based pruning, which is the most popular these days, right? Based on the magnitude for different granularities, okay, which is the most popular approach. And also how to select which neurons to prune. Again, magnitude-based approach is very effective. So now let's switch gear to a new chapter to determining the pruning ratio. Okay. So what would be the sparsity for each layer, and how do we select the sparsity? Okay. So let's brainstorm a little bit. Given a deep neural network, okay, the shallower layers interact with the low-level features, right? Finding the edges, the corners, and deeper layers is finding more abstract information. Which layer do you think has more redundancy? The shallower layer or the deeper layers? Deeper layer, and why is that the case?
We have more features, so there's probably lots of information in each channel.
Yeah, they have contain more abstract features, different images may be different, maybe there's more redundancy and there are more weights, more channels in the later layers. Yeah, that's a very good guess, right? So without a heuristic, right, we can come up with different heuristics which require a lot of fine tuning. So let's see, should we uniform shrink versus non-uniformly shrink the model? So here we compare uniformly shrink all the layers using the same sparsity ratio versus channel pruning. Some layers we get pruned more, some layers we get pruned less. And it's exactly like you mentioned, the deeper layers usually contain more redundancy and can be more aggressively pruned, especially if the neural net has many FC layers. Usually those FC layers can be aggressively pruned, while the earlier layers, the shallower layers, especially the first layer, is usually more difficult to prune. Okay, so this is giving some information about this latency versus this accuracy trade-off. Ideally, we wanna, which point do we want? lower latency, higher accuracy, right? Ideally, we want this one. Using this smartly selecting the pruning ratio versus just uniformly scaling each layer, that matters a lot, differs a lot, right? For example, these two models both has about 70 millisecond latency on a mobile CPU. But if we smartly select the pruning ratio for each channel, it could be like 2% difference with respect to the top point image accuracy, and showing the importance of selecting the proper pruning ratio for each layer. And then the question is, how do we find the ratios for each layer? So we can do some heuristic, like early layer we prune less, late layer we prune more by trial and error. Imagine you have like 50 layers. There will be so many choices. Even if you have like 10%, 20%, 30%, like 50%, if you multiply your choices by the number of layers, that's like n to the power of n, right? So that's a huge amount of choices. So let's do some heuristics. We can analyze the sensitivity, okay, of each layer. What is sensitivity? You prune it a little bit and see how does accuracy drop. You continue prune a little bit more and see how does the accuracy drop, and then do a more aggressive pruning. If the layer is less sensitive, basically you can prune a lot without losing accuracy. But if it's very sensitive, you prune a little bit, and then drastically the accuracy begins to drop. Then for that layer, you want to prune less. Okay, that's the simple heuristic we have here. So let's run this layer by layer and see how does that happen. So here we prune on this Cypher data set using the starter code user in our lab. Or maybe this is the, okay, so let's start with the original neural network. Okay, so which has accuracy, is pretty good accuracy, okay, about 90% accuracy. Okay, and then for the first layer, we gradually prune like 30%, 40%, 50, 60, and then the accuracy begins to drop pretty quick, right? So under 90% of pruning ratio, this is the drop of the accuracy. It's pretty sensitive. Let's see another layer. Okay, so this is the first, this is the second layer, L1, L0, L1, layer 0, layer 1. Okay, this layer is less sensitive until like 70% of pruning, where basically we are removing 70% of the parameters, but the accuracy is still well maintained in this case. Okay, until like 90%, we still drop a very little bit, right? So which means this layer can probably be pruned more. Of course, there are limitations for this method. Well, I walk you through all the layers. Please think about what is the limitation for this method. What did I ignore so far? The correlation between the layers. Yes, that's one of them, right? I am currently analyzing each layer individually, right? And there's one more thing. I will talk about that. So, and then let's see more layers. Okay, L3. Okay, and here is the sensitivity for all the layers. Okay, so some of the layers, like this green layer, is less sensitive to pruning. You can prune a lot without hurting accuracy. Some of the layers are pretty sensitive to pruning, so we should prune less. Then how do we choose the pruning ratio? So let's just give a threshold. Say we want to lose no more than like 5% or 10% of the accuracy. We cut through this sensitivity map and see where is the intersection. Okay? And the intersection indicates the sparsity we want to get. For example, for this blue layer, which is really sensitive, which is cut here, which is about 70 to 75% of pruning ratio. Well, for this less sensitive layer, we can prune more, like more than 80% in this case. Okay. Is this optimal? Of course not, because we are considering each layer independently. assuming the accuracy job is addable with each other. Okay, but actually they tightly interact with each other. So this is the trade-off between how many experiments you want to do versus the approximation. So in real world, even in designing Slider's AI tool or many Intel NVIDIA pruning tools, this is a very widely used heuristic. So if you want to design chips, you want to do some pruning for acceleration, feel free to use this method. It's very robust and easy to do. And can we go beyond these heuristics? Is there a more automated approach that consider the holistic, the whole neural network? So we are going to learn that next. And before moving forward, what is the other limitation if you are targeting the full, the overall better pruning ratio? What is missing here? So far, we talk about the sensitivity, the accuracy perspective. We want to make sure we don't lose too much accuracy for those sensitive layers. What other factors should we consider? Which one should we put more?
Size of the layer.
Exactly, the size of the layers, right? So for example, this green layer, even is very time sensitive, but if it has only a little amount of parameters, pruning that doesn't help us too much. We may as well not pruning that too aggressively, right? But for this, like this red layer, although it's pretty sensitive, but it contributes, say, if it contributes 90% of the parameters, that will help a lot if we just prune it a little bit, right? So that's another factor we want to consider when doing such pruning. So that adds the complexity about the decision making. So an automated approach is very crucial. That's it.
Is it ever possible that accuracy was too simple of a metric to be looking at? So we're like, maybe you prune too much, but 9 out of your 10 classes are fine, but one is absolutely demolished. Like, greater than chance no longer good at recognizing cars anymore.
Right. So designing a proper reward is super crucial. Whether you decide the reward to be just the accuracy, or you have weighted accuracy for individual classes, like a certain class would be super important, right? Or you want to have the false positive versus false negative, you want to reduce them as your end goal, right? So you want to plug in a proper metric. Accuracy is a good metric, but very limited, right? Other metrics also include, like we introduced in the first lecture, the number of weights, the amount of computation, the size of the activation. Those are all the metrics to consider when you are doing the pruning, depend on your scenario. For example, if I just care about the model size, care about if I upload to Apple Store, how long does it take for users to download the model? Then the model size matters, accuracy matters. But if I care about the inference speed, the latency, then the flops matters, and also the amount of data movement matters, right? So that's a good point for different rewards to consider. Okay, so next, which motivates us to the complicated design space motivates us to do such more automated pruning approaches, right? So given the overall compression ratio, how do we choose the per layer pruning ratios? Okay, since the sensitivity analysis ignores the interaction between the layers. And if we have just people doing such work, we can have a couple of customers requiring a model, but maybe 3 engineers can serve 3 customers. Like if we have so many customers, we relying on a lot of engineering efforts to fine tune to find the best solution. So this kind of automated approach, push button solution, let the machines do the job rather than like engineers do the job, is the way to solve this issue. Okay. So traditionally, such pruning require both machine learning expert and also hardware expert, since you want to understand the library, the operator support, which layer is efficient, what is the cache size, etc. And also we want to enable this non-expert to have a push the button solution to enable this efficient neural net design, okay? Bridge the gap with this auto ML approaches. With that, we propose this AutoML for model compression, right? So rather than like human to decide which layer prune how much, now we want to have an agent to automatically figure out how much do we prune for each layer, right? So here we use a reinforcement learning agent to do the job. Okay, so here we have several components. We have a critique, we have an actor, we have an embedding. Okay? So critique, we want to make sure we want to know if this is a good policy or it is a bad policy. Okay, so we want to clearly define the reward function. The simplest reward function would be the error rate, right? We want to have a low error rate. However, that's not enough. We also want to penalize a lot of long latency or a long flops. Okay, we also want to penalize a large model size. Right? So you can add different terms in the reward function. Okay, and what is the action? So action here is the sparsity ratio for each layer. For example, first layer, second layer, third layer, 30%, 50%. What is the sparsity ratio for each layer? And we also need to know the embedding of the neural net, since the architecture of the neural network determines the pruning policy, right? So we will encode those embeddings like NCHW and the index of the layer. Okay, we want to put them into the feature so that the agent can use this feature to give the action. Okay. So in this way, it uses the following setups for the reinforcement learning agent. So when we are designing the states, okay, so there are embedded features, including the layer indices, first layer, second layer, number of channels, kernel size, and flops. Okay. And action is basically the pruning ratio for each layer. Okay. It's a continuous number. That's why we use the DDPG agent. Okay. The agent itself is beyond the lecture of this course. If you are taking a reinforcement learning course, you will learn about this agent. Since it's called continuous action output rather than like up, down, left, right. This is a continuous output, a sparsity ratio between 0 and 1. Okay, and the reward would be if they satisfy your model size constraint, and it will be minus the error. Why minus? You want to encourage lower error rates. Okay, so lower error rate will give you higher reward. Or if it doesn't satisfy your constraint, say you have a 1 megabyte limit of model size, but if after pruning it's still 2 megabytes, then the reward is negative infinite. Okay. We can also optimize for latency, okay, with a pre-built latency lookup table. So this is comparing the human prune model versus offline prune model. Okay, so this is Raspberry 50 on ImageNet. So this one is actually from my PhD thesis, where I spent almost a week to figure out what should we prune for each layer. Okay, from different hand tuning adjustment, spent a week. Allocated pruning ratio for different layer. I got it 29%. Okay, it's pretty good. It's 3 times smaller. But what if we use this AMC agent? Okay. So within just a couple of GPU hours, we can prune it to only 20%. Okay, a much more automated, much automated than human, and also achieve much better pruning ratio. And what's most interesting is that it finds the patterns that really make sense. So this is the pruning policy, which is the sparsity ratio for different layers, altogether 50 layers for resident 50. Okay, and this is the sparsity density, actually the density, the percentage of non-zeros. Okay, so here means very sparse, here means less sparse. You have a lot of non-zeros, versus you have very little non-zeros. So for different stages 1, 2, 3, 4, we use different color to color them. Okay, different stage means different resolution in resident 50. And we can observe something in common for different stages. Okay, so there are those peaks versus crests. Okay. So what are those crests? They are those 3x3 convolutions. Okay, and they are pruned more or pruned less. for those layers? Are they more aggressively pruned or are they less aggressively pruned? Compared with those one by one. They are more aggressively pruned, right? So they have a less number of non-zeros, so they are pruned more. Because 3 by 3, of course, has a larger kernel size, you have more redundancy, but we never teach the agent such rules. Through trial and error, it automatically find that we should prune more for those 3 by 3 convolutions and prune less for those 1 by 1 convolutions, okay? Which is quite interesting. And let's see, what if we prune this mobile net? The original Mac is about 570. The latency is running about 120 milliseconds on the mobile phone. This is a Samsung phone. If we reduce 50% of the flops, the accuracy is well maintained, dropped by 0.1%, but it's 1.8 times faster. Okay? And the memory consumption is also smaller. What if we use this latency constraint? We can use 50% time. We can see immediately the latency is reduced by half. And the top line accuracy is also pretty well maintained. Versus if we naively just linearly scale all the layers by 0.75, we get worse accuracy and also longer latency, which is showing such automated approach is better than just purely linearly scale all the layers. Okay. Let me introduce another approach to automatically find how much should we prune for each layer called net adapt. Okay. The goal of net adapt is to find the best per layer pruning ratio to meet the global constraints. Okay. Let's use this as an example, given a 4-layer neural net to start with. Okay. So we want to define a delta R. So prune the layers. We want to make sure we have a latency reduction of delta R. We try different layers. For example, for first layer, how much do we prune such that we can meet this latency reduction of delta R? We prune more aggressively, finally, we can meet this delta R target. Okay, and then we record what is the accuracy in this case by a short term of fine tuning to see what is the loss of accuracy. And then we try the second layer, prune it a little bit until we can reach this delta R latency reduction, fine tune it a little bit, see what is the accuracy drop. Until we finish that for all the layers, we observe for which layer we can observe the lowest drop of accuracy. Okay. Then we decide to prune that layer in order to meet this delta R latency constraint. Okay. So we repeat this process by pruning, by reducing delta R, 2 delta R, 3 delta R. Okay, each time we want to go through all the layers, try each layer until it reaches this delta R reduction, and then see fine tune a little bit to see which layer has the lowest loss of accuracy given delta R latency reduction. Okay, so in that case, those layers that are least sensitive will be pruned more. Okay? So we repeat this process until the total latency reduction satisfies this constraint. And this method also consistently outperforms different methods, like directly multiply the models by 0.75 or 0.5. Okay. All right, so we now learn how to specify the sparsity ratio. Okay, we learned 3 methods. First method is by this sensitivity analysis, which is very simple, very quick, but doesn't capture these interactions between the layers. The second method is IMC approach using reinforcement learning agents to figure out the best sparsity ratio by the net adapt. To use this per layer delta R analysis to see which layer has the least drop of accuracy. And then let's learn about how to fine tune and train a sparse and prune the neural network, and how do we recover the accuracy after pruning? Okay. A very key point when we are fine-tuning the model is that we need to decrease the learning rate. So since the model is already well trained and almost converged, right? But we nudged it away from this local minimum. But we usually require 1% or 10% of the original learning rate while we are fine-tuning the model. So this is showing the effect before fine-tuning. Okay, so we have seen this one. 80% we have a lot of accuracy drop, but with proper fine-tuning, we can fully recover the accuracy even with 80% of pruning ratio. With showing retuning is super important. Okay, and a good practice is do not pruning the model directly to the target sparsity you want, right? Let's say my target sparsity is 90%. Do not just one step go to 90%, but you want to step by step. Okay, prune a little bit and fine tune it. Prune a little bit and then fine tune it. So we want to prune it 30% fine tune it, 50% fine tune it, and then 70% and fine tune it, which is a pretty good practice, such that we can arrive at this red curve rather than this green curve. And during fine tuning, we want to add regularization to encourage the weights when training the model, we want to encourage the weights to be closer to 0 so that it will be easier to prune them, right? So how do we encourage the weights to be closer to 0? We can add those regularization terms. Okay? So we want to penalize those non-zero parameters by either L1 or L2 regularization. So L1 regularization, you want to add this lambda W versus lambda W squared for these two regularizations. Okay? And these two methods are both very popular in literature and in practice. So magnitude-based fine-tuning applies to L2 regularizations. Other approaches, other papers use L1 regularization. So in our practice, we use these regularization a little bit more, but in practice, they work pretty much equal in both scenarios. Okay, so now we have covered the whole recipe for pruning. Okay, determine the granularity, criterion, pruning ratio, and how to fine tune and retrain the model. Any questions so far? Okay, good. Then let's continue making progress. So let's talk about some recent literature about lottery ticket hypothesis. Okay, can we train a sparse neural network from scratch? Okay. So far, we find the neural network can be compressed, right? Can be reduced. But can we directly train this sparse neural network from the beginning, right? So far, we have to train the model to understand which weight can be pruned. Can we directly train this sparse neural network from scratch? Okay. Some contemporary experience tells us the architectures uncovered the pruning are harder to train from start, reaching lower latency accuracy than the original networks. So this is comparison between two models, okay? And this data set versus on the Sapphire data set, but there's describing similar observation. So the dashed line is basically randomly sampled sparse neural networks. You have a dense network, you randomly sample a subset of the sparse neural network. The more you prune, actually, the lower the accuracy. But there's a solid line that is while maintaining the accuracy, even with very aggressive pruning ratio. What is that line? So you apply the correct sparsity mask. Okay, and how do we obtain this mask? I will talk about later. And use the same initialization, okay, as you are training the model. So initially you are initializing the model, okay, and you train it all the way to the end. When it converges, you find which weight is large, you keep those weights. So you know the sparsity pattern. Those important weights are the winning tickets. They have a mask of 1. Then you apply the same mask to the beginning. When that network gets trained in the beginning, you use that mask, the same initialization, you train it to the end. You can obtain this line that can have a pretty good accuracy, even with only like 1%, 1.2% of the weights remaining. Okay, so in summary here, we can recover the accuracy by using this lottery ticket hypothesis, which is basically saying a randomly initialized dense neural network contain a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. So this is just an illustration. We have a randomly initialized model. The initialization is colored in light blue, okay? And we train it for the p epochs, and then the weight becomes the dark blue. And the winning ticket is basically saying we find the magnitude of the trained model. Okay? We keep those large magnitude weights. So those are the winning tickets. Those magnitudes that are large, after training, you have to train it to the end to find those winning tickets. And those winning tickets, you want to initialize the original weight using this light blue color, showing that it's not reusing that weight, that converged weight, but you are using this initialized weight, but apply this sparsity mask. Okay, and you can train this model for at most t epochs. You can obtain the same accuracy as before. So this is the illustration. We are initializing the model, we train it, and then we prune it based on the magnitude. We prune away those small magnitude weights. Okay? And then we re-initialize the model using the same initialization and using that sparsity pattern. Okay? Observe that model and this model, they have the same sparsity pattern, but they have different weights. That weights is during conversion, is already converged. So this is the initialized weight. Okay, so use this weight, but use that sparsity pattern. And then we train it, and then we prune it more. So notice that the sparsity of this model is already more sparse than this one. Like this edge is removed in that case. So we gradually prune more during this case, and then we apply the same sparsity mask during convergence to this model. Okay, so it becomes sparser, but using the same initialization. This is light blue, not dark blue. This is light blue as the original model, and then we can train it. Finally, we can obtain the same accuracy, although this model has the same accuracy, much smaller than the beginning model. So the tricky part is we still have to train the model when it converges to get, in order to get this sparsity mask. Okay, so there is a scaling limitation where resetting the weights to the very initial value. It works for those small scale tasks like MNIST and CIFAR, but the deeper networks on ImageNet actually does not work. But instead, it is possible to robustly obtain a proved set subnetwork by resetting the weights not to T0, but after a small number of k training iterations, which we need to manually explore, rather than rewinding everything to WT equal to 0. We want to reset it to WT equals to k. Okay, so that we can still recover the accuracy on large scale data sets like image. So this is showing like rewinding to epoch 0, the accuracy is decreasing pretty fast. But if we rewind it to iteration 6, okay, to epoch 6, we can better recover the accuracy. So So the total number of training epochs is 90, but we are reminding to epoch 6.
How big an effect does the data set have on the sparsity?
So for the, how does the data set scale matters for the mask?
So I given one architecture with the sparsity mask to be like wildly different.
Actually, it's quite different. Exactly. So like ImageNet, it's in the sparsity pattern. You lose accuracy when you are reaching like 16%. But on MNIST, if you go back, the sparsity ratio is actually really aggressive, like 1 or 2%. And on Sci-Fi 10, it's like 7%-ish. So the sparsity is really depends on the complexity of your data set. So ImageNet is very complicated, so it makes sense where we can prune less. Well, MNIST is so simple, like in last lecture, in our demo, right? We can prune all the way to like 90, 95%, 99%, right? So it's really dependent on the data set. Let's continue to talk about the algorithm hardware co-design and also the system support for sparsity. So conventional paradigm is that you train the model, okay, and then you obtain the model, and you directly deploy the model for inference. So what's the drawback for that? So we are using this convex optimization, right, which is SGD, to deal with such a highly non-convex model, which is the neural nets. So a lot of redundancy and over-parameterization is actually required to make sure we can have a good convergence. Okay? And actually, the model is super over-parameterized, very inefficient for inference. So if we directly deploy that, it will going to consume a lot of unnecessary memory and computation, which could be super slow on mobile devices. So a better approach, a better paradigm is actually after training, you do not directly deploy your model for production, but rather you want to compress the model and remove those redundancies, remove those over-parameterization, get a more compact model, and then run it through accelerated inference with specialized hardware, which is fast and also is more power efficient. So here we have 3 very fundamental rules. Okay, so anything multiplied by 0 is 0, right? So if you observe any of the weight is 0, you don't have to compute the computation, right? And after random function, if the activation is 0, you also don't have to multiply that. And thirdly, for deep neural nets, we don't need that high precision, 2.09, 1.92. You just approximate everything by 2 and using quantization, which we're going to cover in Thursday's lecture. So we want to take advantage of those weight sparsity. Okay, weight sparsity, 90% of the weight are 0. So you want to definitely not multiply, save the computation, right, x, but say 5x less memory footprint. Why is less compared with the computation? Since we need metadata to represent the sparse matrix, we want to store not only the weight, but also the index or the bit mask. Okay? Worst case, it will be around 2x less compared with the saving of the computation. And also for the activation, we usually can get like almost 70%. This is run through, this is due to the redo function, where after redo, you get a free food for many zeros. Okay, but this is dynamic, where compared with weight sparsity, where after pruning, no matter which image, which input comes into inference, the sparsity pattern is the same. But for the activation, the sparsity is determined at the runtime. Okay, so that's the difference. So you cannot actually save the memory due to you don't know what is sparsity pattern, but you can achieve less computation. Maybe future also smarter ideas can also enable saving for the activation, since you can use smarter data structures to represent those activations. And finally, by weight sharing or quantization, we can easily quantize the neural net to 4 bits for the weight only. Okay, so that saves about 8 times compared with the 32-bit floating point representation, which we're going to dive deeper into next lecture for quantization and weight sharing. So after pruning, okay, so the weight matrix becomes super sparse. Okay, so here it is, we have a vector of size 4, and the matrix is 8 by 4. Okay, you see a lot of the weights are actually proven to be 0. Okay, this is a simplified matrix. Okay, and the output, this is the bias for the output, and the output dimension is 8 in this scenario. Okay, so an 8 by 4 matrix, input is 4 by 1, and output is 8 by 1. Okay, so we want to analyze how do we parallelize, how do we skip those zeros. Okay, so efficient inference engine is the first accelerator that can take advantage of the weight sparsity for prune the neural network with the weight sparsity. So we first map it to different processing elements. Okay, so each color indicates a different processing element. So here in this example, we have 4 processing elements. Okay, and first process P is responsible for the first row and also the 5th row. Okay, the second one is responsible for the second row and also the 6th. Okay, so on and so on. Okay. And physically, they are stored in this way. Okay, so for the metrics, for example, given P0, which is the green PE, so we want to only store those non-zero elements. In this case, W00, then W01, W42, W03, and W43. Okay. And also, we want to store those relative index. What is their position? The first one is actually 0. And then W01 is immediately after that. Okay, so we put a number 1. Okay, so W42, which is here, we have two zeros in between this W01 and W42. So we have number 2, and then W03 is immediately after this W42, therefore we have 0. So this is showing the relative index, the gap between the previous non-zero and the current non-zero. Why do we use such relative index rather than the absolute index? Less storage, yeah, exactly. So if the absolute value is pretty large, and you have 4K, you need many bits to represent the absolute index. But using this relative jump, this difference is fewer number of bits. And finally, you have the column pointer. And you want to show which is the starting point and end point for each column. So you have for 4 columns, you have 5 numbers. So you want to indicate not only the starting point, but also the end point for each column. Okay. So for example, in column 0, we have only 1 element. Therefore, immediately the starting point of the second column is location number 1, okay, W01. And the starting point for the third column is number 2, which is W4. Okay, so that is the column pointer. This is how we represent the sparse matrix. This is adapted version of the CNC, compressed sparse column format. And now you understand why the memory saving is less than, if you prune it by 90%, the saving of memory is less than 10x, because you have this metadata to store, not only those non-zero weights. Okay. Any question?
I didn't quite understand why do we start with the first row and then suddenly go down to the second row and then back up
rather than this row, right? So we are having different processing elements.
Yeah.
So this is one group, and this is a copy of another group, a copy of another group.
But why do we order the virtual weights this way? So why?
Oh, so this corresponds to PE0. So this is the green PE. This is also corresponding to the same PE. All the PEs are processing element in lockstep. So you have a same copy for PE1 for this purple PE, right? Another similarly for the blue PE. And this is just one out of 4 processing elements.
While we declare the column pointer, we can manually calculate it right, from the relative index.
For the column pointer, you don't know which one is corresponding to the starting point of a new column, right?
But we
You
can-
know the distance between the different, you know the number of the distance between different non-zero weights. For example, W01 and W42, W01 and W42 differ by 2 locations, but I don't know whether it's a new row, new column, or it is an old column.
But if we know that there are only 2 rows, then we can anyways guess the column. Right?
So you don't know actually how many rows you have. So here, we didn't have any number indicating in this case, we have 2 rows. Okay, so the data flow to ignore 0 is like this. So we started with the activation. We observe whether the input is 0. If it's 0, then we skip that. Okay, if it is a non-zero, okay, like A1, it is non-zero. Then we are going to broadcast this non-zero weight to all the different PEs. Okay, so they are processed, they are broadcasted to all the PEs, and then in parallel, they are multiplied and added with a bias and then update the output. We encounter another 0. What do we do with that? We skip that. We skip the entire column, not having to do any computation on this 0 activation, so that we can take advantage of not only the weight sparsity, but also the activation sparsity. If the activation after value is 0, then it doesn't have to be multiplied with any element with the whole column. Okay. And after that, we find another non-zero element. So we broadcast it to all the PEs that has non-zero elements. Okay, actually, the first cycle we updated the first half, and the second cycle we handle the second half. Okay, and finally we update the output. So in order to support that data flow, this is the microarchitecture for each processing element to accelerate such sparse and pruned model. So we have activation queue. Okay, so we can see different PEs. They may have different number of non-zeros. So we want to make sure that they are balanced and make some buffer. Okay, and then we deal with this activation sparsity by examining whether the output is 0, the input is 0. Okay, if it is non-zero, then we pass it through the weight matrix. Okay, we have, just like they mentioned, we have this column start and end address, and also the sparse weight matrix. Okay, so we find those non-zero elements and then decode the weights. So we will talk about that in the next lecture about weight sharing and weight decoding. And then for the address, remember we are storing those relative index. Therefore, we need to accumulate them to get the absolute index. And then we do the multiplication, add, and also have the address in parallel. Therefore, we can store it into the corresponding location and update the output as run. Okay. So actually, the key computation is this multiplication add, but we have to do a lot of actual work to guide where should we read and where should we write. Okay. And finally, we pass it through the read unit and detect if it is 0 or non-zero. Even if it's non-zero, we are going to put it in the activation queue of the next stage. So the special part is the activation queue. We want to do load balance, and also we have the weight decoder to turn a 4-bit quantized index into a 16-bit real weight value, and also this address accumulator to turn a relative index into an absolute index. So this is the layout of the efficient inference engine. And this is the sparsity ratio for TiE can handle FC layers only. Okay, so this is the FC layers for LXNet. With sparsity, activation sparsity, this is the flop reduction by multiplying the weight density with the activation density. These are the FC layers of the VGG model. These are the image capture model, the neural talk. Okay, so we observe that why the activation density for these are 100. Actually, they don't use red one. That's the reason we don't have the activation sparsity for these image capture models. Okay, so they're using sigmoid. That's why we have a less flop reduction for these models. Okay, and it's pretty decent speed up compared with the CPU and GPU. And these models are actually compressed. So even on the CPU, running the compressed model can have a pretty big advantage over the non-compressed model. So this is measured on the FC layer of LXNet, VGG, and neural talk. And this is comparing the energy efficiency of CPU, GPU, mobile GPU, and the efficient inference engine. And we can find in general, running the compressed model has a pretty big advantage over the non-compressed model. So this is an early prototype back in 2015, 16. But a couple of years later, in 2021, when NVIDIA A100 came out, this technique has been solidly commercialized in NVIDIA GPU, where it is supported 2-to-4 sparsity. Okay, so after TiE, we made an FPGA prototype to accelerate not only this FC layers, but also this recurrent neural nets, which is widely used in speech recognition, image caption, machine translation, and VQA. So let's talk about speech recognition. So previously we do compression and then we do accelerated inference on top of the compressed model. Okay, so we want to rethink the design flow, whether when we are designing the accelerator, what should we do? Can we do better when we are doing pruning? Okay, can we co-design the pruning algorithm versus the inference engine? Okay, so here we find load balancing is a very critical problem. Okay, so in this case, this green PE has how many non-zero entries? If it is dense, it should be 4 + 4, 8 entries. But it is sparse. In this case, it has 5 entries, taking more cycle than the PE3, which has actually only 1 non-zero element. Okay, so the total number of cycles is dependent on the largest PE, which has 5 non-zero elements. So when we are doing pruning, this is telling us we should prune them such that each PE roughly has a similar amount of non-zero elements, rather than this PE has to wait for this PE, right? So this is the guidance from the hardware to the pruning algorithm. So we want to run such load balance aware pruning, where each PE, we want to make sure they have roughly similar number of non-zero elements. Okay, in this case, the green PE has 1, 2, 3, with 3 non-zero elements, similar for the orange and others. Okay. And as a result, overall cycles is very balanced. But this is actual constraint we have to add. Does it hurt the accuracy? That's really the case. So we did this analysis. This is without load balancing. So we can do roughly 90% of the parameters without significantly increasing the phone error rates. But if we apply this load balance aware pruning, we can still achieve a similar pruning ratio, okay, without increasing the error rate much. Okay, so by using such load balance aware pruning is quite helpful. But comparing the speedup, remember when we are not load balanced, there will be some extra work. Someone has to wait. The so fast PEs has to wait for those slow PEs. Therefore, we have a 5 by 5x speed up. But if we have load balance aware pruning, we can actually have a higher speed up, okay, 6.2x speed up over the dense model without hurting the accuracy. So this is really showing that this algorithm hardware co-design where the hardware features actually guide better software pruning. The pruning algorithm will lead to a better speed up without changing the RTL. So this is exactly the same hardware, exactly the same RTL, but can achieve a better speed up with a more properly pruned model architecture. So this is overall building blocks, memory units, sparse matrix multiplication units, and also these element-wise units. So this is prototyped on this FPGA. Okay, that means AU6 FPGA. This is comparing the latency with the GPU and CPU. Those are back in 2016. So we plateau at the max. So now we have much better full efficient GPU. And the power is power consumption versus speed up energy efficiency. Such a specialized model, it's really having a higher power efficiency. But really another factor is super important for deep learning computing is the programmability, okay? And also how easy the software is to adapt to diverse different model architectures, right? So I want to show in this slide all the pros and cons for such specialized accelerator, right? This is back in, I designed this in 2017, right? So later, actually 1 year later, this transformer models came out, right? BERT came out, okay? And the deep learning community is just evolving so fast, right? So programmability and adaptation capability and flexibility is super important. So when you are dealing with AI inference engine, AI chips, and AI hardware, this flexibility is the top thing to keep in mind as a part with the efficiency and also the speed up. Okay, so this would be a good advice for not only the software but also the chip designers. We want to make sure our models are our hardware, the silicon, is coupled with very well organized and easy to be adapted the software stack. Okay. All right, so let's fast forward to 2021. Okay, 5 years later, it's very exciting that the sparsity, pruning, model compression has landed in NVIDIA GPUs. Okay, the GPU sparsity is now natively supported using a adapted version, which is M sparsity. And what is M sparsity? In this case, this is 2 to 4 sparsity. So in every 4 elements, okay, in every 4 elements as a group, at least 2 of them has to be 0. Okay, you can have 3 zeros, you can have 4 zeros, but you have to at least have 2 0 elements. Okay, so this is for the first block, and similarly for the second block, we have 2 middle points that is non-zero, and all the other 2 is 0. 2 out of 4 are 0. 2 out of 4 are 0. So every 4 elements, we have at least 2 zeros. So that is 2 to 4 sparsity. How do we represent that? So we can condense these 8 entries into only 4 entries. So 2 to 4 sparsity, we can at most 4 non-zero elements. And we have to store the index, okay? The index for each element. Okay? Whether this element can come from 4 locations, 0, 1, 2, 3. And we need to store 2 bits for each non-zero element, indicating where they are. For example, for this one, we have to store 0 since it is in the first location. For this one, we'll store 3 since it's in the last location. That's why we need 2 bits per entry to store the index, the location for each non-zero indices. Okay, so just a quick question. For this element, what should be its index for this element?
Or, yeah, 0, 1.
Yeah, actually it's 1, right? And this is 2, right? So 0, 1, 2, 3, and you are storing 2 bits indicating its position. And how do we accelerate it? It's very smart, in NVIDIA GPU to support the 2 to 4 sparsity, dense case, sparse case. For the dense case, you can have a pruned model. This is the weight, this is the activation. You have to do 8 multiplications. Okay, you accumulate them to get this input A matrix. This is the B matrix. Okay, you multiply them together, you get this row, multiply it by this column, you get this entry. Right? This is the basics of matrix multiplication. You have 8 numbers, you have to do 8 multiplications and 8 additions. That's the traditional scenario, right? 8. What about the updated version? For this weight matrix, we are no longer storing in the original format, but in the sparse format. Okay? Out of these 8, only 4 of them are non-zero together with this index. So we put them here. For the first operand, we put it in the 4 non-zeros. And for the corresponding activations, we want to have the exact same sparsity pattern. Since 0 multiplied by anything is 0. You will see non-zero, 0, 0, non-zero. Similar here, non-zero, 0, 0, non-zero. So we want to pick the corresponding element by using this index, right? So in here, what should be the index? For example, this non-zero element, this is 0, 1, 2, 3. 0, 1, 2, 3. So the index is actually 0 and 3 in this case. So here we are showing 0 and 3. We use that as a selection to select 0 and 3 from the activation. Okay, so that these 2 are skipped. Out of these 8 elements, only 4 of them are selected using these 2 bits for each one. Okay? So therefore, we can just multiply the 4 numbers with these 4 numbers, put them, accumulate them together, and get the final output. Okay? Very smart. 8 numbers now becomes only 4 numbers that we need to multiply and accumulate. Okay, theoretically save you 8 half of the cycles. Okay. Any questions on the data flow? How NVIDIA supports sparsity?
What is the cost of the index?
Actually, this is pure combinational logic, right? Very little data movement. Okay? So such things can be completed within like 1 cycle or something. So it should be very low cost.
So if the matrix has even a single case where there's more than 2 non-zero values in a given sector, is it completely invalid and you can't use any of it, or
it will be ignored, right? So if you have 3 non-zeros, okay, then we only have the capacity to store half of the entries. So during pruning, you want to make sure the software engineer will prune the model such that you have at least 2 non-zeros, at least 2 zeros out of 4 entries.
Assume we have certain schemes for selecting the ratios, right?
Yeah, you can do 2 to 4, like 3 to 6, 3 to 9, etc.
So they have a set of the ratios they use.
So far, I'm only aware of 2 to 4, since 4 is friendly, and where you have it's 2 to the power of 2, right? If you have 3 over 9, then it's hard to make it byte aligned. But of course, I think you can have more aggressive, like 2 to 8 sparsity, if you can have better pruning algorithm to make sure you have a more aggressive pruning, but also well-maintained accuracy. The larger the n, the harder to maintain the accuracy, but the higher the potential to have more speed up. So that's the trade-off.
does the entire model have to be pruned to 2 for sparsity, so you have like particular layers accelerated with this, and then some layers take the full extent of it?
Sorry, what's the question again?
Like, is it possible to have like some subset of the model accelerated with sparse calculation while the rest don't have 2 for sparsity and have to take the full calculation? Or is it
Yeah,
better?
of course, yeah. So A100 support both sparse and dense operation. If some layers are dense, of course, use the original methods to accelerate to run that. That's totally possible. Actually, the first layer of a neural net sometimes is harder to prune. So sometimes people choose to run it in dense format. All right, that's a lot of good questions. So just another good example to observe what's the difference between the first academic prototype and also the industry product, right? And how exciting it is, the short amount of time from 2015 where the paper is out versus in 2021, you can actually get a physical silicon in production. Isn't it very cool? So this is showing the speed up for the GMM. So this is sweeping over the K dimension. So MK times K N. And we can observe the larger the K, the higher the speed up. Essentially, it's at about 2, since it's 2 to 4 sparsity, you save at most 2x. And on the right-hand side, it's showing the accuracy across different models, mostly vision models. And the accuracy is actually well maintained using the sparse version versus the dense version. And why 2 to 4? That's also one reason is due to we want to fully maintain the accuracy rather than 2 to 6 or 2 to 8 sparsity. All right, so summarize today's lecture. We learned about automated ways to find the pruning ratio, right? Very practical method is using the sensitivity analysis. And we discussed this fun part, which is the lottery ticket hypothesis. Both of these are directions could be a good direction for your final project, right? Continue exploring either of these directions. And also we discussed this system support for sparse. In the next lecture, we will talk about quantization, another very important concept in efficient deep learning. First, introducing the data types, RP16, what is RP8, RP16 in 8, and basic concepts of network quantization and common quantization methods. Here are today's references for today's papers we covered today. And that's all for this lecture. Thank you.